Today's lesson is on series circuits. When we're connecting components together to make a circuit, we can connect them in one of two different ways. Okay. First option is a series circuit. Okay. This time of year, some people are starting to already set up their holiday lights. Okay, and there's two types of lights. Christmas lights are in series. Okay. If you got Christmas holiday lights, like on a Christmas tree, and one of them burns out, all of them go out. Okay, so series circuits is where there's a single path. Okay, this is most Christmas lights. All right, so that if one burns out, then there's a break in the circuit, and then all of them burn out. Okay, parallel circuit. Okay, is more akin to, let's say, a Hanukkah menorah. Right, a Hanukkah menorah, you can, if it's a light up one as opposed to a candlelit one, you can turn, or you can light one on and the other one's off. All right, so when they're in parallel, there's multiple paths for the electron where the lights can go through. So the example of a parallel circuit is, let's say, a Hanukkah menorah. And these components, these boxes right here, represent components, and they could be resistors. Okay, resistors could be, for example, lights, okay, Christmas lights or Hanukkah lights. Okay, could be batteries, capacitors, all sorts of different objects that cause great resistance. Kirchhoff discovered two things about electrical circuits. Kirchhoff first discovered the voltage law, which says that all of the voltage drops in a series circuit are equal to the total applied voltage. So if you've got a 9-volt battery, that's the total applied voltage. That means, and you've got three bulbs that it's going across, each of those individual bulbs voltage drops are going to have to add up to that 9 volts in the 9-volt battery. Kirchhoff's current law relates to parallel circuits. That says that the total current, right, which is the flow of electrons through the circuit, is equal to the sum of each of the individual branch currents. So basically, the currents add up. All right, the first example that we're going to focus on today, as I mentioned, is what's called a series circuit. Again, it's like a conga line. Okay, it has only one path for current to flow. The electrons have to go in one direction. Remember, we said electrons want to go from negative to positive, so the electrons go negative to positive. All right. If the path is open anywhere, the current stops flowing. So, for example, let's say if one of the bulbs breaks or somebody cuts this line by mistake, our conga line gets broken, right? And our conga line no longer works, so the electrons can't flow, basically. So our entire circuit will stop. Right, so here's our break. Okay, again, like a Christmas light. So some characteristics of a series circuit are that the current is equal. Okay, in a conga line, everybody has to go at the same speed, otherwise your conga line breaks apart. Okay, current is basically how fast the electrons are flowing. Okay, so current has to be the same. Okay, remember that current goes from positive to negative because current is actually opposite the way the electrons go. Total resistance is equal to the sum of all resistance. So if we have one resistor that's 220 ohms and another that's 470 ohms and another that's 1,200 ohms or 1.2 kilo ohms, to get the total resistance in this whole circuit, we add them up. So we would do 220 plus 470 plus 1,200 will give you the total amount of resistance, total resistance. So in a series circuit, resistances add. Now all these formulas are in your formula sheet, so you don't need to memorize it. Also in a series circuit, Kirchhoff's voltage law says that voltages add up. So the voltage across a resistor 1 plus the voltage across resistor 2 plus the voltage across resistor 3 have to add up. So in a series circuit, resistances add and also voltages add. Again, these are both in the formula sheet. So here's another example of a series circuit. Okay. All right, so we've got one resistor, it's 220 ohms, another one 470, and another one 1,200 ohms. Okay, the current, as we said, current's always the same. Okay, and the voltages add up. We use those results to verify Kirchhoff's voltage law. So here's our example. It's the same circuit we just showed you. Okay, Well, R1 is 220, R2 is 470, R3 is 1,200. So if we add all those up, we get 1,900 ohms. Again, this Greek letter omega represents ohms, which is the units for resistance, so it gives us 1.9 kilo ohms. Normally, if there's a resistance that's greater than 1,000, we usually write it as kilo ohms. The current through each one, well, current, we use Ohm's law for that. All right, so current is equal to voltage divided by resistance. Well, our total voltage is 12. All right, so our voltage, our numerator is going to be 12 volts. Our total resistance, we said, is 1,900 ohms. So our current is going to be 12 volts divided by 1,900 ohms, right? And that's going to give us 6,300 amps. Oh, I'm sorry, 6.3 times 10 to the minus 3 amps, which is 6.3 milliamps. All right, milli is 10 to the minus 3. 10 to the minus 3. All right, so that's how we can calculate current. Since this is a series circuit, current's always the same. Remember, current is how fast the electrons are flowing. And current in a series circuit is like a conga line where they all have to be going in the same speed. Okay, so the current has to be the same all the way around. That's another way to look at that same series circuit. The voltages have to be the same. So voltage is equal to I times R. So if I'm trying to figure out what the voltage that's going to my first resistor, is that current that we figured out, which is 6.349 milliamps times 220 volts. That means V1, the voltage that drops across resistor 1, is 1.397. So this one is 1.397 volts. Okay. Now let's go ahead and do the same to figure out what's the voltage that goes across the second resistor. 6.349 times 470, that gives us 2.984. 298, okay? That's volts. And now let's do the last one. Okay, 6.349 times 1.2 kilo ohms gives us 7.6 volts, 7.619 volts. So the total voltage would be adding all those up, 1.397 plus 2.984 plus 7.618. And when we add those up, okay, we end up with 12 volts. So what we did is we just demonstrated that we did our math correctly. The great thing about doing series circuits is that if you do all your math correctly, you can double check your work at the end, and you'll know even before you submit your quiz or your homework assignment that you've already got it correct. Okay, so there's our lesson on series circuits.